Okay, so one of the big applications of vectors is representing motion. Okay, now motion by itself is not particularly useful unless we look at it in terms of time. Okay, so what we're looking at here when we're talking about parametric equations is we're going to be using vectors to model, in our case, a linear motion. We are not going to get into more complex ones where we have a vector that is, parabolic in nature or something like that, or changing. But what we're dealing with here is we add this parameter of time to a situation. And what happens here is we represent both x and y and z, if we're in 3 dimensions, as separate functions relative to time. Okay? And then not only do we get a location, but we also get a time of when we were at that location. All right? And I like to use the illustration of, if you modeled all of you moving around this room this period, okay? At one point, your path went through that door, okay? And if I were just to draw your path and we looked at it on a map, we would see, here's the door, here's Anna came in and sat there, and then we had someone here, and then they came over here, and then sat there, and then this person was over here, and, if I just did that, it looks as though we had a pile up right here in the doorway, okay? But I didn't see anybody tripping over anybody or running into anybody over there. And the reason is because all of you, while you did go across that path, all of you had that location at a different time. Okay? So that's one thing that can be a challenge here, is to see, okay, we may have 2 objects where their paths crossed, but then the question is, well, did they actually meet each other? Okay? Another illustration is like an intersection, all right? When you're driving your car, if you were to model everybody's motion through the intersection, you have all these crossing lines, all right? And hopefully all the times are different and we don't have any accidents, all right? So, but just to illustrate how we do this, here's a very simple example of a pair of parametric equations, okay? For parametric equations, you do have to look at them in pairs. Like here we have an x equation and a y equation. You might see it written as x of t and y of t because they are both functions of t. All right? But if I want to figure out for different times, like here the time is going to go from -2 to 3, and yes, you can have negative times. 0 is just when we happen to start the clock, but the object may have been moving before we started the clock, so we can kind of go back in time and figure out where it was. All right, so if I want to look at this one, I would plug a -2 in to the x equation. So it would be -2 squared minus 4. 4 minus 4 is 0. Okay? But the y equation is t divided by 2. So if I want to figure out what my y coordinate is, I've got to do -2 divided by 2, and I get -1. Okay? So now I have a location at 0, -1. And one of the things that we're going to do with this is we would label the point with the time, so t equals a -2. Alright, and then we would work our way through all of those points. At -1, I'd have a -1 squared minus 4. 1 minus 4 is a -3. -1 divided by 2 is obviously just a -1/2. So I'm at -3, -1/2 when t equals a -1. And then we keep going, okay? At 0, I have 0 squared minus 4, so -4. I have 0 divided by 2, which is 0. So I have the point -4, 0 when t equals 0. We'll do all of them different colors if we can. At 1, I have 1 squared minus 4, -3. I have 1 over 2, which is just a half. So right here is when t equals 1. At 2, I have 2 squared minus 4, -2. 2 divided by 2 is 1. So I have the point here, -2, 1. Okay? Oh wait, shoot. I forgot to square the 2.
Yeah.
That would be 0, 1.
Yeah, I was gonna say it's not.
Yeah. Feel free to speak up if I do something stupid.
No, I would.
All right.
So like you said.
All right. So we've got that, and then what do we want to use? Yeah, that's an ugly color, but it's different at least. All right. So we got 3 squared minus 4. 9 minus 4 is 5, and 3 over 2 is 1.5. So 1, 2, 3, 4, 5, 1.5. When t equals 3. Now, if I'm going to model this motion, I label the times, but also it can be helpful to draw an arrow to kind of indicate which direction we're going. See how I did that? Now, that's not a required part of the graph, but it can be helpful. But that is basically how you would sketch a graph in Parametric. We don't do a lot of sketching, but I want you guys to understand how this is working, because it's helpful when you're interpreting the situation or trying to figure out what's going on in the situation. Okay? Does that make sense? So that's what a set of parametric equations is. All right, it would be both of these equations combined make one graph. Okay. All right, so let's connect this idea of parametric equations to 3 dimensions and look at how we would write equations of lines and equations and parametric equations that represent lines in these situations. Okay, so here we have a parametric equation, or we have this line that's drawn over here. This is the line that we actually want. Okay, we want it to go through this point 1, -2, 4. Okay. And we're given this direction vector. Now, a direction vector is not bound to a location. You guys know that. Vectors are not bound to a specific location. But basically what we want is we want this line L to be parallel to that direction vector. In other words, we want it to have the same direction. Okay? So, what we're going to do is we're going to we are going to use both a vector equation and a parametric equation, or set of parametric equations, in order to do this. So we're going to kind of develop this over the next couple slides here. All right, so first of all, let's start with the parametric equations. It says here, if I have a direction vector, ABC, and I want my line to go through the point x sub 0, y sub 0, z sub 0, okay, then the parametric equations are going to be x equals x sub 0 plus at, y would equal y sub 0 plus bt, and z equals z sub 0 plus ct. Alright, so you'll notice what we're doing here is we take the starting point. The reason why we have x with a subscript of 0 here is because this is our horizontal position at time 0. Okay? And y sub 0 is our y position at time 0. Okay? And it makes sense here. If I plugged in a 0 for t, then x would just be x sub 0. Right? So, if I'm given a point, remember we said time was kind of arbitrary. It doesn't matter when we start the clock. So what I'm going to do is I'm going to let t equal 0 for this point that I'm going through. And what that's going to mean is that x is going to be 1 plus 2 times t. Now I got the 2 from right here. So every second, or every unit of time, my x is going to increase by 2. Okay? That's all there is to it. The y is starting at -2, and every unit of time it's going to increase by 4. I'm saying since this is the only point I know, I'm going to say that the time when I'm at that point is 0. So I'm going to use that as my starting point. Basically, whatever point you're given, use that as your starting point.
They're all just 0 because A times 0 is 0, B times 0 is 0, C times 0 is 0.
Yes, at this point. At this one point. But as I plug other times in, I'll get other locations. Okay? Here's z. I'm starting at 4 when time is 0. But then, notice z, every unit of time is going to decrease by 4. So I have z minus 4t. Those three equations together are the parametric equations. You got to have all three. So what we're saying is we're at this location when t equals 0. When t equaled 1, just to illustrate here, if t equals 1, at t equals 0, we're at 1, -2, 4. If t equals 1, 1 plus 2 times 1 is 3. -2 plus 4 times 1 is 2. And 4 minus 4 would be 0. So, we would be at the point 3, 2, 0. So this point right here that I just drew is that point when t equals 1. Okay? So you can see this line, even though it's kind of hard in 3 dimensions, this line is kind of cutting down through this XY plane right there after 1 second. Okay? And again, it's hard to see, but the nice thing is we're not going to work with having to actually see these very much. We're just going to be working with the equations the vast majority of the time. Okay? So let's take this one step further and incorporate the vectors a little more directly. All right, we just saw these parametric equations. All right, here's an equation, the vector equation of a line, and this is what shows up in our formula booklet. Okay, the vector equation of a line. Notice what each of these is. The equation R is our position vector at any given time. Okay, so that's telling us where we're at. What's our location? A is the position vector at time 0. Okay, so A is where we're getting these values from. Okay? Also, if you look down here, that's what we have. Okay, that's our position at time 0. Kind of color coding all these just to help you make the connections. B is our velocity vector. Now that is this A, B, and C. Okay? Or down here in this, A, B, and C. Okay? And then, of course, T is how much time has passed since we started the clock. Okay? Does that make sense? As long as you can make those connections and keep straight which one is your position at the starting point and which one is your velocity, it's really not too difficult. So on the previous example, we had the equations x equals y equals z equals, what were those equations again? Do you guys have them written down? From the previous example that we just did. X was
1 plus 2t.
minus 2 plus 4t.
minus 2 plus 4t is y. 4 minus 4t is z. Okay, so from this, we knew, just to make the connection here, A is our position at time t, so that's the vector 1, negative 2, 4. It's a position vector, so we're writing it as a vector from 0 to the point would be that. Okay? And then the velocity vector, we were told, but even if we weren't told, just looking at this equation, the velocity vector would be 2, 4, negative 4. Okay? Again, that comes from here, here, and here, including the minus. Okay? Our starting position was these numbers right there. Okay, so if I were writing the vector equation, I would write it like this. Our position, R, at any given time equals 1, negative 2, 4, plus T times 2, 4, negative 4. Okay? That's our component vector form, or the vector equation of the line. Alright? And basically, here's what you need to be able to do. if you're given the component vector form like I just wrote, you should be able to write down the parametric equations. If you're given the parametric equations, you should be able to write down the vector equation. Okay? Alright, so let's practice this for a second and make the connection. I gave you one with only 2 dimensions just to start here. Okay? We have x and y instead of x, y, and z. Alright? What would our starting position be? What point are we starting at? No, according to this equation right here, xy is negative 2, 5 plus t times 2, negative 1. Yeah, the negative 2, 5. Okay, so negative 2, 5 would be our starting position. Okay? What would our velocity equal? I'm going to write this as a vector. What's our velocity? According to this equation, Chenian, do you know? What would our velocity vector be?
Is it like one number or like
Or, I don't know.
You guys are way overthinking this. Should he join us and put your phone away?
2.
No. This. There's only 2 vectors here. There's a starting position and there's a velocity. Okay? So this is our starting position, guys. Our velocity is 2, negative 1. Okay? That's our velocity. Every time t increases, we're going to the right 2 and we're going down 1. Which is a whole lot like slope, right?
Yeah.
Okay? Now, the parametric equations, we should have how many parametric equations in this case? 2, because we have 2 dimensions. So x equals and y equals. So what does x equal?
X is 0 plus a2. So, like,
Negative 2
So negative 2 is the x sub 0,
minus 2t.
not minus 2,
I mean plus 2.
plus 2t. Okay? You take the x from your starting position, the horizontal component of your velocity, negative 2 plus 2t. Okay? How about my y? Y equals
5 minus t.
5 minus t. Let me give you a little tip here. This is where the notation can be helpful. Alright, using an alternate form of the notation. If I use the notation like this, you can see, hey, my horizontal parametric equation is just negative 2 plus t times 2. And the y is 5 plus t times negative 1. You just kind of go across the rows. So that may be helpful, especially in 3D. That alternative form might be useful. Okay? So let's find some points. Okay? So when t is 0, 0, 1, 5, negative 2, those are the 4 points we want. X is negative 2t, negative 2 plus 2t. So negative 2 plus 0 is negative 2. Negative 2 plus 2 times 1 is 0. Negative 2 plus 2 times 5. Negative 2 plus 10 is 8. And negative 2 plus 2 times negative 2 is negative 2 minus 4, which is negative 6. So those are all the x coordinates of these points. the y coordinates, I'm just doing 5 minus the time. So 5 minus 0 is 5, 5 minus 1 is 4, 5 minus 5 is 0, 5 minus a negative 2 would be 7. Okay, so notice here, I have these points, 0, 4, negative 2, 5, I have 5, 8, I'm sorry, not 5, 8, I have 8, 0, and I have negative 6, 7, so 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, okay? But notice here, this was when t equals a negative 2, this was when t equals 0, this is when t equals 1, and this is when t equals 5. If I track that motion, I'm on this line. Okay? But again, it's going this direction if I follow the times. Okay? Now, this last part here is the part where the application really comes in. I want to find out, hey, at what is the time and the y value when x equals 10? So this is 8, 0, 9, 10. Alright? So basically I'm looking for this point here. I know it's the point 10 something.
So you just do 10 plus negative 2 plus 2t.
Okay, yes. Alright? Yes, absolutely. X is 10, so 10 has got to be
T equals 6.
negative 2 plus 2t, and then I solve that and I get t equal to 6.
And then you plug it in for y.
Then we can plug it in for y.
Or minus 6.
Okay? So now I know y is 5 minus 6, negative 1. Okay? This is how you can use these parametric equations. Alright, if we're talking about motion, we want to see when it passes a particular point. That may just, we may not really care where the y is. We just want to see, hey, when is it going to pass this certain x? We can use the x parametric equation to figure out that time. And then if we want, we can plug the time into y to figure out exactly where it's going to be. Okay? This is how they figure out, now it's not linear, but trajectories of things like, hey, if I shoot this thing at this target, is it going to clear this other building that I don't want to hit? You know? If we're shooting a rocket at some kind of a target, we want to hit it, not the building in front of it. So trajectory matters, right? So I've got to figure out, hey, is it going to land here? Yes, but if it's coming in at an angle like this, am I going to hit my target? No, I'm going to hit the building in front of it. Okay? So then we'd have to adjust our trajectory so it was coming in at a steeper angle or something like that. Or if you watch football, you see kickers get their kicks blocked, not because they weren't going to kick it far enough, but because their trajectory was too low to clear the offensive or the defensive line. So, all right. Okay, one last problem, and then we're going to go ahead and then we're going to look at our topics here. Okay. So one of the questions that we have here is, does an object pass through a specific point? Okay. Now, as I look at this, again, I might want to rewrite this in a little different notation. So I have a negative 2, 5, 7 plus t times 2, negative 1, 4. Because what will help here is to write our parametric equations. So x equals, y equals, and z equals. X is going to be negative 2 plus 2t. Y is going to be 5 minus t. And then z is 7 plus 4t. Now, if it passes through the point 2, 3, 15, what's going to happen? Or how would I be able to tell if it's going to pass through this point?
Two equals negative 2 plus 2t, or
Okay, if you solve this, you'll get t equals what? You add negative 2. Okay, you're going to get 2. Because you add 2, you get 4. 4 divided by 2 would be 2. Okay? So do I know if it hits the point yet? No. Okay.
well, then you have to solve the rest of them so you can have t equals 2.
That's the key right there. You guys hear that?
Mhm.
I would have to be at that x, that y, and that z at exactly the same time. I mean, yes, y will equal 3 at some point in time. Y, 3 equals 5 minus t. Well, there t equals 2. Alright, so far we're good with x and y. Let's try the z. It's got to equal 15. So 7 plus 4t. I subtract, I get 8. 8 divided by 4, t equals 2. So since these are all the same, the answer is yes. When t equals 2. Okay? However, if I tried it down here with this one, negative 8 equals a negative 2 plus 2t. I add 2, I get negative 6 equals 2t. T equals a negative 3. It's okay that that's negative, but let's check the y. Alright, 8 equals 5 minus t. So that's going to be t equals a negative 3. So far, so good. So let's try the last one. Negative 1 equals 7 plus 4t. I subtract the 7 and I get negative 8 equals 4t. I divide by 4. I get t equals negative 2. So I don't actually hit that point because my z will not be right when my x and y are right. Okay? So no, because the times are different.